Hello everyone. So today we will talk about some practical examples which we need to be able to do after studying a course in machine learning. So it's some practical examples. I mean, we need to be able to work with images. We need to be work with time series, for example. We need to be able to work with text, for example. So those are the most important areas of applications of machine learning. So today we will not talk about anything new, in fact, but I will show you some examples. Some of those examples I solved it already, and I had some code for it, and some of those examples are not solved. Um, so we need to talk about images. If you want to work with images, this is very famous, in fact. Maybe in your project you will be working with face recognition system. You need to develop a system for face recognition. Maybe you need to develop a system for object recognition or object detection, for example. So there are many applications with images. I mean, machine learning are very good with images, in fact. So I give you an example last time. It's about face recognition. This is the project which you need to develop and submit. Face recognition using Olveti dataset. There are also lots of public, there are lots of public datasets, in fact. So for example, we can talk about CIFAR 10 and the CIFAR 100. And also there is something called the color facial recognition technology dataset. It's also important to be able to work with text. I mean, when we are working with text, there are many applications. We can work with something, they call it sequence to sequence. Those sequence to sequence, it means a translation. For example, if we need to build a system for text translation, we need to translate a text from Norsk to English, for example. So the input to the machine learning will be a sequence, and the output will be a sequence. So this is an example of working with text. There is something also called sentiment analysis. In this sentiment analysis, we have a sequence of text, and we need to convert it into a single value. So I have a text, for example, and we need to decide, is it positive or is it negative? So it could be reviews, for example, of movies. We have an example here, Internet Movies Database. So it's reviews about movies. So people, when they watch a movie, for example, they just write a review, and we need to check, because millions of people are writing those reviews, and we need to decide, is it positive or is it negative? It could be also, we have a bank, or we have a kind of production, and we have reviews from customers, and we need to check, is it positive or is it negative? It could be used for recommendation system. So I mean, we need to build a recommendation system for marketing, for example, and we need to decide how many people are supporting, how many people are criticizing, for example. So in this case, we will have a sequence of text, and we need someone to read this text and decide, is it positive or is it negative? So in fact, in the binary, in this case, the output in this case will be binary, be 0 and 1, for example, if it is negative or positive, or any other sentiment analysis. We can have something also multi-classification. So for example, news, for example, I mean, we can extract news or tweets from Twitter, for example, and we need to classify into some topics. Is it in politics? Is it foreign affairs? Is it economy, money, religious, and so on? So we can classify the text into a set of topics. So working with text is very important, but working with text, it's very challenging, in fact. We need also to know how to work with time series, because in time series, this is very important. In banking systems, we need to predict what will be the price of stock price, for example, next week, tomorrow, using historical information. So working with time series is one of the most important areas also in machine learning. So we have here two examples. We have one called the Boston housing data, and those Boston housing data, it's using some features from the area, for example, neighborhood area of houses, and they can decide what will be the price of this house. We have also airline passengers. Airline passengers, it's a number of passengers in airline, I guess in 144 data points. So it's like in 144 months, for example. So we can use historical data to predict what will be the next value. And of course, in those time series, we should expect to see those seasonal impacts and stuff like this. So also it's not an easy task, but of course working with time series is very, very important. So we need to know different types of applications, and we need to practice. How can we work with those examples? So we used this home assignment, face recognition. Last time we used this Olfiti data set or database. This Olfiti database, it consists of 40 images, 10 images, I guess, for 40 persons. So in total, we have 400 images. And we use 10 images because we need to be sure that we will be able to recognize a person in different orientations, different directions. So usually people prefer to take several images, maybe in different light conditions and in different directions, and they classify it as that person. So in this case here, we have 40 persons. We had a project last year, bachelor project. So students were trying to build a system for to allow people to get access to a building using images. So it could be something like this one. It should be something, they call it OpenSet, for example, because in OpenSet, we will allow the system to add new people when we got new people working in the company, for example. So we need to give them access. So it should be possible to add people and remove people to your system. So this Olfiti example, so the idea here was to, we can just upload this Olfiti faces from sklearn, and after that, we just upload the data, and I plot the data here using a grid. So the idea was to display your data set, for example. Each image, it's 64 times 64 pixels, which is huge, in fact. So the first point here, the first task was to divide the data into a training and validation and testing with shuffling, because it's in order, in fact, for those 40 persons. So we need to shuffle the data, and we need to divide it into a training, a validation, and testing. Because the image size, it's 64 times 64, so the number of pixels will be very huge, correct? So in this case, I was proposing here to use PCA, for example, for dimensionality reduction, and also if reconstructing the images using a subset of features, it will be very, very good. So for example, we will have here 64 times 64, which will be, I will just check how many features we have. So when it's 64 times 64, so in total it will be 4,160 features, correct? So it's too much. So if you will build a model here, you will build a model with 4,160 inputs. So it will be smart, and not all those pixels are very important, correct? So maybe not all pixels carry the same amount of information. So it will be smart if we can try to use principal component analysis for dimensionality reduction. You can just select, for example, I will select the top 100 eigenvectors. So those are the eigenvectors with the highest eigenvalues as principal components, and I will use those 100 values to reconstruct the image one more time using this subset of features. So the idea here is to use principal component analysis, and after that, select maybe the top 100 principal components, and using this subset of features to reconstruct the image. So we will use those for reconstructing the image one more time. I guess we studied last time autoencoder for dimensionality reduction. So also I recommend also that you can try to use the autoencoder for reconstructing those images. Autoencoder, it's unsupervised, and it's just a feed-forward neural network, and the number of inputs should be equal to the number of outputs. So the input will be an image, and the output will be an image, and in the middle we will have a bottleneck. This bottleneck, it will give us a code. This code, in fact, it's a reduced set of features. So instead of using PCA, which is a statistical tool, in fact, we can use a feed-forward neural network, and we can train this the autoencoder to reduce the dimension to code the image into a subset of features, reduce the set of features. And in the same way also, we can use the decoder for reconstructing, right? So the autoencoder, if we need to plot the autoencoder, it will, if it is 2 layers, for example, so the hidden layer will be the code, the one which will generate the code. For example, maybe it could be, for example, 64. If we will go for 64, and the number of inputs will be the total number of pixels. So we will start by, for example, I will call it x1, x2, and finally we will have x4160. Make all those connections. Make all those connections, and the output will be, the output layer will be a layer which has the same number of outputs as the input. So we will have, for example, y1, y2 until y4160, and we will just train this feed-forward neural network as normal, right? So the input will be an image, the output will be an image. We will calculate the error at the output. This error, we will call it reconstruction error. When it's feed-forward neural network for regression, we call it regression error. When it's for classification, we can just say it's a prediction error, for example. But when it's for autoencoder, we call it reconstruction error. So we will train this one using my data set, and at the end, we will slice it into two sections. We will extract the first layer, because the first layer, in fact, this is the encoder. So we will take this encoder and we will apply it to my data. So when we apply an image of the size of 4160 pixels, we will get a subset which is 64 pixels, representing my image. So in this case, we are reducing the dimension of my data using an autoencoder. So in this point, we need to use PCA, principal component analysis, and in the second point, we need to use an autoencoder. And in both cases, you need to reconstruct the image using a subset of features and just make comparison. I suppose also you can try to use an supervised algorithm, for example, and supervised algorithm. Supervised algorithm, it could be, for example, it could be KNN, for example. We can try to use key nearest neighborhood, or just multi-layer perceptron, correct? And in case of unsupervised, we can just use K-means clustering. K-means clustering algorithm. It should be just a try, And of course, after training your model, we need to evaluate our model. We need to evaluate the performance of our model. So we need to plot the confusion matrix. Also, in this example, you can just decide to, maybe you can just say, okay, I will try to use cross-validation or hold-out validation. So, and make comparison. So I wrote here cross-validation, but you can try cross-validation, and you can compare it also with, I don't know why it's not full screen. So, so you can try cross-validation and hold out validation, for example, and make comparison. You can try stochastic gradient descent, batch gradient descent, and mini batch gradient descent. And in this case, you can check, time, for example. How much time do we need to run to train our model? How much time? This is very important, right? How many epochs, for example? So you need to make good comparison between all those models. Yes. So here so this is Olfetti data set. So if you want to work with Olfetti data set, you can do a lot. You can do many things. If you want to work with another data set, we have something called the CIFAR10. The CIFAR10, also you can load it from Keras datasets, .CIFAR10 or CIFAR100, and it's a data set which consists of 60,000 times 32 times 32 color images. So each image, in fact, it's 32 times 32 pixels. So we have 60,000 images, and each image, the image size is 32 times 32 pixels. So the image is 32 times 32 pixels. And it's classified, we need to classify it in 10 classes with 6,000 images per class. So we have 10 classes. Those classes are airplane, it's images for airplane, for example, cars, bird, cat, deer, dog, frog, horse, ship, truck. So we have 10 classes. So at the end, we need to build a model which can classify all those images into one of those 10 classes. So the data set is divided into 5 training batches, and the test batch, each with 10,000 images. So it's already divided into batches. So you can go for mini batch, batch training, for example, batch gradient descent. The test batch contains exactly 1,000 randomly selected images from each class. The training batches contain the remaining images in random order. So it's already shuffled and it's already prepared for you to train your model. So this is also something very important. So this is a very good example. If you want to work with images, so you can just go for CIFAR 10 and develop a model for classifying each image into one of those 10 classes. So you need to select. I propose or I suggest that you can go for Keras, for example, and build your model in Keras, and try, for example, start with a base model where you have one hidden layer and one output layer, for example. 32 times 32, so total number of features will be 32 times 32, so it's 1,024 features. So the number of inputs will be 1,024 features. So you can select, for example, the number of units in the hidden layer to 512, for example, or 256. And of course, the output layer will have 10 outputs because we have 10 classes. In this example, you can use one-hot encoding. When you use one-hot encoding, so you will have 10 outputs, right? So when it's airplane, for example, it will be 1 and the rest will be zeros. When it's car, it will be 0, 1, and the rest will be zeros, and so on. So using one-hot encoding here is very important. If you will go for Keras, you can just use, the hidden layer, activation function of the hidden layer, it could be rectified linear unit, and the output, it will be softmax, for example. So this is how CIFAR. I guess I made one. I made also in GitHub a file. I just prepared it, just uploading the data, and just loading the data from CIFAR, and just plotting some pictures. So it's already there, in fact, in GitHub. And also I used the two categorical here to generate the one-hot encoding of Y-train and Y-test. So it's ready, in fact, for. So you just need to select your model now. You can select your model. It's normalized already. So each pixel value has been divided by 255 to be between 0 and 1. And it's one-hot encoded, in fact. So the outputs or the classes labels are one-hot encoded. So in fact here you can go for autoencoder also if you want to use dimensionality reduction. So you can try principal component analysis if you want. You can go directly for the data as it is, and you can try to use principal component analysis. You can also try autoencoder. So we have also CIFAR 100. CIFAR 10, we have 10 classes. CIFAR 100, it's just 100. We have 100 classes. We have in fact a superclass and the subclasses. For example, in Fish, there are many subclasses in each main class. Yes. Anyone has any questions? So you can go for CIFAR 10 and you can go also for CIFAR 100. It's just the scale up. We scale up the problem for a larger data set and make it more complex. So it's a good example. And also CIFAR 10, you can download it from keras.datasets. So it's not. We lots of data sets. In fact, this data set, I don't know if this data set can be downloaded from keras.datasets or sklearn or not, but you have a link here. You can just download this data set and upload it. This data set, it's 8.5 gigabytes of faces. It's for face recognition, color face recognition. So it's 8.5 gigabytes of faces for training facial recognition software. And it consists of more than 14,000 images. For around 1,200 individuals. So this data set, it's very challenging, and it's really very good data sets. You can go for Olfetti, for example. Now we are working with Olfetti data sets. It's only 40 persons, right? This one, it's much larger. So if you want to scale up, you can go for this one. You can also, I propose that you can use autoencoder, because autoencoder, it's very smart for denoising, for example, and the dimensionality reduction. So if you feel that there are some noise, you can train an autoencoder for denoising and of course, for dimensionality reduction. So I don't know what is the size of each image here, in fact. So you need to go to the link and check how many pixels in each image. So do you have any questions for the images? Any questions for images, if you want to work with images? It's a very straightforward, and it's very similar to MNIST dataset, because an MNIST dataset, it's a grayscale image of size 28 times 28 pixels. So it's more or less it's the same, but maybe we need to have more complex model for those complex datasets. But I mean, when you develop a pipeline, we can just apply the pipeline to any kind of datasets. So images are very important, because maybe in your bachelor project you will be working. I mean, we had some people last semester, for example, working with fish. Some people working with face recognition for security reasons and stuff like this. So there are many applications for images. So working with images is very, very important. So maybe you will get, for example, an image where there are a number of objects. So you need to detect the object location, and you need to classify it, for example, count it, quantify it. So maybe I need to count how many objects, how many apples in an image, for example, how many cars, and so on. So I mean, the second part, in fact, it's about text, because working with text is very, very important. Working with text is very important. We have been working with social robots, for example, and in the case of social robots, we need to translate Noshka into English and English back into Noshka again. We need also to build a dialogue system. So in this dialogue system, the robot is dealing with the patients or people in verbal way, right? So we need to understand the text. So in fact, we build a dialogue system, and we collect text, and from this text we can apply, for example, sentiment analysis. So maybe the robot is talking to one person this morning, and maybe this person is sad, is happy, depressed, correct? So maybe we need to understand this. We need to decide. We need to understand, to identify if the person is sad or happy or depressed, positive, negative. So it's a kind of sentiment analysis. So we talk with a person, we collect the text, and we need to train a machine learning model. We need to send the text to the machine learning, and the machine learning will say, okay, this person is sad today. So in this case, we need to consider this. Maybe we can say a joke, for example. We can say something funny to change his mood, for example. We need to identify from the text. So we call it sentiment analysis. And in sentiment analysis, it's a binary classification problem, just a binary classification problem. So the input to the model will be a sequence of text, right? So it's a sequence of words, and we need someone to say, okay, this is negative, this is positive, this is 1, this is 0, for example. We call it sentiment analysis. So because machine learning cannot work with text, we need to replace we need to give each word an index and replace each word with a number. It could be an integer number, right? So this is a task. So if I want to say, of course, how are you, for example, and I want the robot to say, okay, how are you? How are you? So how can the machine learning understand the meaning of how are you? So in this case, we will change how with a word with a number, R with another number, index, word index, U with a word index. So we need to build a dictionary, and we need to decide how many vocabularies we will use, for example, and assign a word index for each word. In this case, we can convert any sequence of words into a sequence of numbers, right? If you have a book, I can just convert this book into a list of numbers or a vector of numbers. So if you have for a A4 page full of text, we can convert it into a vector of numbers. We can use, later on, we can use one-hot encoding, any kind of encoding. We can use autoencoder for dimensionality reduction. There is something called word embedding, for example. So, but first we need to assign word index to each word and convert each sequence of words into a vector of numbers. Because machine learning cannot understand words, but it can understand numbers. Because in those calculations, we are just using numbers. So the input to any machine learning model must be numbers. Image, for example, image, it's numbers because we have pixel values. So it's the same way. If we are working with text, we need to convert this text into numbers. So here in this example, we have something called IMDb. IMDb, it stands for Internet Movie Database. It's Internet Movie Database. And it's 50,000 movie reviews for natural language processing or text analytics for binary sentiment classification. Each review is a sequence of words of different lengths converted into a sequence of integers. So if you have a sequence of words, we need to convert it into a sequence of integers, where each integer stands for a specific word in a dictionary. We need to build a dictionary, for example, up to 10,000 words, for example, and we will give each word an index. And if you have any text, you can convert this text into a sequence of integer values. For example, we can select the top 10,000 most popular words which we are using daily, for example. So we will have a filter, in fact, and we will keep only words which we are most common, right? Because we don't need this dictionary to be very large. For example, if you want this, and after that, you will change each word with an index. So in this case, if you have a text, for example, a recording or whatever, you can convert this one into a sequence of numbers, integer values. So I can normalize it. I can convert it to another form. Now it's numbers, so it's easy to deal with. And we need to build our database. So if you have those reviews, we need to label it because we are working with supervised learning, for example. So I need to label it. So I need someone to just read this one and just say, okay, this is positive, this is negative. So if you are watching a movie and you wrote something, for example, so he will, hey, this comment is positive. This comment is negative. So we need someone to label those reviews. So now we are building a database for supervised learning. The problem here, not all people are writing the same length. For example, someone he will write one sentence, someone else he will write one page. So the size will be different. To fix this case, we can select, as I told you, we can select the top 10,000 most popular words, for example. So in this case, we will limit each review into 10,000 words, ignoring repetitions, for example, right? Because if I have a word which has been repeated, so we will just ignore this. We will represent it only one time. So, and we will remove words which does not exist in the dictionary. So in this data set, we have 50,000 reviews, 25,000 for training, 25,000 for testing, and each set consists of 50% positive reviews and 50% negative reviews. Positive reviews will be represented by 1, and the negative reviews will be represented by 0. So in this case, we can just use Gaussian activation function because Gaussian will give us number between 0 and 1, right? Each review, it's a sequence of words, will be converted into a vector of 10,000 dimensional vector of zeros, except for word indices. I have each review. We agree that each review will be converted, will be maximum 10,000, right? Because we limited ourselves to 10,000 words, most popular words. So in case maximum, it will be 10,000. So we need to vectorize it. We need to convert it into a vector of integer values. So we will replace each word with each index, correct? And it will be 1 in that index and 0 otherwise.
Yeah.
So for example, you will build a vector. I mean, we have index, right, of words. So we will start from 0, 1, 2, 3, 4, 5. So I can just write it here. So we will have 10,000 words, right? 10,000 words, and we will convert it into a vector. So this vector will be like this one. Word number 0, word number 1, 2, 3, and so on until 9,999. And we will check. If I have this word which has index 0, we will put 1. Word number 1, we don't have it, it will be 0. Word number 2, we don't have it, it will be 0. Word number 3, we have it, so it will be 1, and so on. So it will be like this. So at the end, we will convert each review into a vector of a binary vector of ones and zeros. It will be 1 when we have. It will be 1. It will be zeros except for word index. It will be zeros except for word index. And of course, in this case, repetitions will not be considered. So in this case, this data set, which is 50,000 reviews, it will be converted into a 2D tensor of shape 50,000 times 10,000, right? It will be like this. So now the data set will be just numbers. It will be numbers, right? If you are not happy with 10,000, because now each row will be 10,000. It's like MNIST data set. Each row was 28 times 28, which was 784, I guess, right? So now each row will be 10,000. So if we are building a machine learning model for sentiment analysis, so the input size will be 10,000. Maybe it's too much, especially because we will have many zeros. So if someone he wrote, a very short review, for example, so the majority of the vector will be zeros. So too much zeros, which is not very important for us. So in this case, we can reduce the dimension of this vector, for example, using autoencoder or using principal component analysis. Correct? So we can convert it into a subset or a small set of, reduce the set of features. So in this case, we can reduce it, and instead of working with 10,000, we can convert it into 1,000, for example, or 500. So I have this example. You have this imdb.Python. It's in GitHub. So I uploaded my data set and I restricted it to 10,000 words. So we have here, when we're uploading it, we upload this one from, we upload this data set, and we have the data set already shuffled and divided into training and testing. We restricted ourselves to 10,000 to make it manageable. We vectorize my data set, we just prepare it, and finally we will get something similar to this one. So this one to the left, it's a sequence of words. It's one example of a review. This one, it's a review, right? This one, it's an example of review. So when you are watching a movie, maybe you will go and write a review, for example. This review, the machine learning model cannot work with this one as it is. It's impossible, right? We need to convert this one into numbers. So we will limit ourselves into 10,000 most popular words. We will give each, we will tokenize it. So we will give each single word an index. So for example, this, it will be 1. In this example here, this, it will be 1. Film, it will be 14. Was, it will be 22. Just, it will be 16, and so on. So we will give each word an index. And this one, it will be coded into this sequence of integers. So this review, it will be converted into this one, right? Of course, the size of this one will be the same size, the same number of words. So the size of this one will be the same number of words as this one. So if you have here, because each person, he will write a different review, so the review length will be different. So maybe this one, I don't know how many words in this one, but imagine that it's 2,000 words, 2,500 words. So this one also will have the same size. It will be 2,500 integer values. But now we will have a problem, because some people are writing 3,000, someone will write 200 words, someone will write 2 words. And you can just say, okay, this movie is shit, for example. So it's just 3 words or 4 words. So some reviews will be very long, some reviews will be very short. So this is a problem in inconsistency. Inconsistent, we need to be consistent, which means we need to have the same number of inputs each time, because when we are building a machine learning model, we need to have the same number of inputs fixed. To fix this problem, we will convert this one into this form, right? We will convert it into this word. So we will have a vector. This vector, it consists of, has a size of 10,000, right? 10,000 values. It will be a binary vector. So we have the index. So the index of the first location, it will be index 0, 1, 2, 3, 4, 5 until 9,999. And if you have the index 1, we will put 1 at the location 1. If you have 14, we will put 1 at 14. If you have 22, we will put 1 at the location of 22, and the rest will be zeros, correct? The rest will be 0. In this case, when you look into this vector, it will have a fixed length. It will be 10,000, and it will be fixed for all reviews, right? So now we are converting each review from a sequence of words into a sequence of integer values, and after that into a sequence of binary values. So this one will be a sequence of binary values, right? So now we have a fixed length, a vector of a fixed length. So now we can just build our machine learning and train it. So the input will be this vector, and the output will be the label. So the label will be 1 and 0, right? The output will be 1 and 0. 1 when it's positive review, and 0 when it's negative review. So it's a binary classification problem. In fact, we are just doing a binary classification problem. I built the model, in fact, and I built a model using Keras, right? So this one, it's 1, 2, 3, 4. It's 5 hidden layers, and we have an input layer. We have 5 hidden layers, and we have output layers. The output layer is sigmoid, and the output is 2. We have 2 outputs, right? Because we have 2. I used one hot encoding for the output. So the output will be, for example, 1 and 0 when it's positive, and 0 and 1 when it's negative, right? Number of inputs will be 10,000. Do you see input shape? The input shape is 10,000. Why? Because the input vector here, the input vector will be 10,000 values, binary values. As I told you, if you are not happy with this vector, you can use principal component analysis, or you can use autoencoder to reduce the dimension of inputs or the number of features. Activation function, just select any activation function. Anyway, I mean, it's not very important to use ReLU, but because we use the very many hidden layers, ReLU is fine. You can use linear, for example. But anyway, all values, all input values are between 0 and 1. It's just zeros and ones. It's binary inputs. We use the binary cross entropy loss function, and we just trained the model, and we tested the model. And the accuracy we got, in 3-4 epoch, in 3 or 4 epoch, we got 87% accuracy, right? So we have accuracy of 87%. So this is very good example. This is very good example for working with text, right? So, but of course, maybe here we have some, I don't know if we have some overfitting or not, but this dot once, it's a training and validation. This one is very important to check if you have overfitting or not. And as you can see here, the solid line here, the blue line, it's a validation loss. This is the validation loss. So the validation loss, in fact, it goes down, and it looks like that it goes up. And the training loss, it was high value, and it's decreasing, which is okay. I guess it's fine. I mean, maybe there is no overfitting, maybe very little overfitting. But of course, we can overcome this overfitting by reducing the dimension of the input shape, input vector, this one. So we can simplify the model. We can make it more simple. So I propose that you can repeat this example, but repeat this one using autoencoder. So try to use autoencoder and try to reduce those 10,000 values into maybe 1,000 or 500. So in this case, the number of parameters here will decrease. Do you see in the first layer how many parameters? I mean, we selected 1,024 units multiplied by 10,000 plus 1024. So number of parameters is huge. So maybe we should expect that the model will overfit. If you want to fix this problem, you need to play with principal component analysis or autoencoder to reduce the dimension of the input features or descriptive features. So this is very, very good example. I mean, the second example, it's multi-class classification example. It's the same, but it's using this Reuters data set. It's in use short news wires and their topics, and it was published in 1986. In these data sets, we have 46 topics. I mean, in sentiment analysis, we have only 2 topics or 2 values, positive and negative. But in this news wires, we have 46 topics, different topics. And in each topic, we have at least 10 examples in the training sets. So the data set is not very big. So, but it's multi-class classifications. You have many classes. It's not binary classification. So it's the same, no problem. We will use also one-hot encoding. So we will build a machine learning models where we have 46 outputs, correct? But it's the same way. We need to do the same with the text. Machine learning cannot understand the text. So we need to convert this text into a vector of numbers, float numbers, for example, or integer numbers. So this is an example. This is one news wire. This one text. And it's the same problem also. Not all news wires have the same length. They don't have the same number of words. So we will convert this one into a vector of integer values. So it's the same. We can create a dictionary. We can limit ourselves also to the first, the top 10,000 most popular words, and we can create our dictionary. So in this dictionary, we will have 10,000 words. We will give an index to each word. We will convert this one into, we will replace each word with each index, correct? And after that, we will convert this one into a vector, and this vector consists of 10,000 binary values. This one will be 10,000. The length will be 10,000 values. And it will be 1 when in the location of 1, for example, 0 otherwise, 1 at 2, 1 at 8, 1 at 43, and so on. So we can convert it into a vector of 10,000 binary values. This one, it's because this text, for example, it's topic 3. So when it's a 3, it will be 1. Otherwise, it will be zeros. So this one, it will be it's 46 values, binary values. It's one-hot encoding. So it will be 1 when it's index 3 and 0 otherwise. So now we are prepared our data. The input is a vector of 10,000 binary values, and the output will be this vector, which consists of 46 values. So now we are just ready for training our model. So it's in the same way. If you want, you can use principal component analysis, or you can train an autoencoder to reduce this one more, because this one is too long, in fact. So when it's too big, we will have too much numbers of weights, and then when the model has many weights, the model will have much bigger capacity, and the chances to overfit will be very, very high. I did it, so you will have also the code here. You can just go to the code and change it. Try to modify it. Try to develop it more. So try to use principal component analysis. Try to use autoencoder, for example. And as you can see here, the number of parameters here is huge, in fact. The number here is huge. Why? Because I selected here 128 units in the first layer. So it will be 128 times 10,000 plus bias 128. So it will be this number. So in fact, if you can reduce the dimension of the input feature, if you can reduce this one, you will reduce this one, I mean, a lot. And then when it's reduced, the chances to overfit will be really very, very, very low. So I'm expecting that this model also will overfit. Yes, it's a clearly overfitting problem. If you can look here into the training and the validation loss. So the training loss, do you see? So the training loss, it's going down. It's fine. It's okay. We should expecting this. So it's going down, which is fine. But when you are looking into the training loss, so the training loss is going down also. Yeah, it's going down. No, it's fine. It will be a problem if it will go up again. So it will be overfitting if this validation, no, sorry. I just mixed it. So those dots are training loss. So the training loss is going down, which is okay. The problem here is that the validation loss, it's going down, and after that it goes up a little bit. And if we will keep training, maybe this one will go up like this, which means it's overfitting problem. We can see it also in the training and validation accuracy. For the training accuracy, accuracy goes up, which is normal. We are expecting this. So when you are training your model more and more, this one will go up. Here we have validation accuracy, it's going up, and after that, it looks like it's going down a little bit. Maybe if we continue, it will go down or not. So it looks like little overfit. But as I told you, if you want to fix this, you need to reduce number of parameters, model parameters. When we reduce the model parameters, we try to restrict the model. We try to reduce its capacity to memorize my data points. Or you need to increase the size of your data points. So in this model here, I used the dropout with factor coefficient 0.5. So we use dropout. Dropout, it's one way for dealing with overfitting. So finally, we need to work with time series. We have here an example, Boston housing data. Those Boston housing data, it's a very nice one because it's like if you want to build a system, for example, in Olesund to predict home prices, because just people or meglars or owners, they decide by themselves, for example, but you can collect information, historical data from all meglars. You can build a mobile app, for example, or AI service, for example. So people can just put informations of their homes and it can give them prediction, for example. So this is the same. So in this data set, we have, in fact, 13 features. We have 13 descriptive features, right? So, and we try to predict this one, number 14. We try to predict median value of owner-occupied homes in $1,000. So we try to predict number 14. So in fact, we are using 13 values to predict number 14. So this is one example. It's like regression model, in fact. So you have 13 factors or variables, and we're trying to use those 14 variables to predict what will be the home price, for example. Median value of the home price. So this is very important. You can download it from GitHub. In fact, I have this Boston housing price dataset. I put it, in fact, in a GitHub. I made a GitHub for it. And also you have, if you want to get the dataset, you can get dataset from this website. So you have the dataset. I made a GitHub already with maybe plotting. I don't know how much I did in this one, but it's a very, very simple one. Number of examples is 506, right? You have 13 attributes. You have 13 attributes to predict the median value of owner-occupied homes, and it's in Boston. And I guess this data was collected in 1980 something. So this is very good application. We can build a similar application if you can collect information from Olesund, for example. Maybe I mean I guess you know better than me. You can, if you can get data set from Norway, for example, we can build similar applications, and we can make it. We can make an API so people can just get access to it and try to use it for evaluating their homes, for example. I think someone is writing something. Please, if you have any questions, just inform me. But now we are finishing. So this data set for time series prediction, in fact, it's airline passengers data set, and it's an example of time series. So it's given a year and a month. The task is to predict number of international airline passengers in units of 1,000. So we have here the prediction in 1,000. So this one, it's a prediction. And because the time series time is very important, so we need to keep it. We cannot just shuffle it in somehow. So maybe this one, it's months or a year, for example. It's collected from January 1949 to December. So it's 12 years of data. So those one, it's 12 years of data. in months. So we have those, we have here time, right? And we have here, I mean, number of passengers, number of in 1,000 unit. And it's important, I mean, if there is a company want to expand, for example, so, or if they want to estimate their income next year, for example, sometimes it's ups and downs. Maybe it's winter time, summer time, for example. I mean, if you see here, maybe this is seasonal impact. So when we go here, for example, it could be seasons, right? Maybe it's too much in summertime and it's low in winter time, correct? So those numbers. And its pattern, which is repeated because it has this, so the idea here is to try to predict next year, for example, how many passengers we should expect next month. So the idea here is to predict what will happen next, right? So it could be something like this one, what will happen next month or next year and so on. So the goal here is given the current time, we want to predict the value at the next time in the sequence t+1. So if you got the value here at t, for example, if we got the value here, so what about t+1? 140 plus 1. So next month, t+1, maybe it's next month, for example. So given the value at t, what will be the value at t+1? You can make it more complex also. So given the values at t-1, t-2, t-1, for example, and the t, what will be the value at t+1? Correct? So we can create a window, and we can use this window of values to predict the next value, for example. So this is very exciting data set. So you can select a t, you can select the historical value at t to get t+1, or you can use maybe the last 5 values to predict t+1, for example. So you just need to organize it in this way, for example. So here I'm using all the 3 values or the last 3 values to predict the next value. So I'm using those 3 values to predict this one. And after that, I'm using those 3 values, which is 118, 132, 129 to predict this one, and so on. So in this case, in fact, it's quite simple because I will have a hidden layer of any number of units. This is not a problem. And we will have, for example, 3 inputs. So it will be, for example, I call it xt minus 2, xt minus 1, and xt to predict what? To predict, in fact, xt+1. So it will be organized like this one. You can build a neural network for doing this task like this one. You need to divide your data into training and testing, but as I told you, because time and order is very important. When it's time series, we need to consider order. We cannot mix it because order is very, time factor, because we're collecting those data, in time. Each month we are just collecting data, so time is very important. So we cannot just mix it, we cannot shuffle it. When it's a data time series, we cannot just shuffle and just mix it. It will be a problem. So we need to, for example, select from 0 to 100 for training, and the rest will be for testing. So this part will be training part, and we will try it. We will use it for testing. The values here. So this one will be testing. So when it's time series, you cannot just mix it in somehow. It's very important to keep it in order, right? Because time is very, very important here. So you have also airline passengers. In fact, you have the code here. So you have the code here. You now just need to go to it, run it, and try to make some changes. And if you have any question, you can just ask me. So now we finished. In fact, you have those examples. So just please go to those examples and try to implement by yourself. And if you have any questions, just ask me those questions. You can answer it. So now we are finishing this machine learning part, and the next week we will start in the expert system part. We used 8 weeks for the machine learning part. It's not bad, in fact, because machine learning is very, very important. But the rest of the time, we need to study maybe an optimization algorithm or 2 optimization algorithms and an expert system. We need to build an expert system. We will study rule-based system. So for the machine learning part, to sum up, you need to study chapter 6 in the book. You have this book, Artificial Intelligence, A Guide to Intelligent Systems. So please go to this book and read chapter 6. It's only one chapter, in fact, right? Neural network, but it's a very basic one, very, very basic one. We covered more topics, in fact. We covered more topics. I mean, in this chapter 6, I guess he just talked about feed-forward neural network, perceptron, and perceptron learning rule. So it's a very, very basic. Maybe also he explained error backpropagation in a simple way. So it's only one chapter. So we spend, in fact, 8 weeks in one chapter. It's not one chapter, but because we are studying from this book, so it's one chapter in the book. But we covered much more, in fact. We covered much more. To study those topics, you need to go to the slides, in fact. You just go to the slides and just read those topics very well. We covered many topics in this part. We covered a perceptron learning rule, multi-layer perceptron. We studied gradient descent. We studied error backpropagation. We studied how to deal with separable and inseparable data sets. We studied dimensionality reduction using principal component analysis and using autoencoder. We studied some data pre-processing, scaling, and standardization. Very, very important. Very important to know the equation, and very important to know why you are doing it. We studied activation function, several activation functions. We need to know what is the difference between all those activation functions. Why do we need to use ReLU, for example? We studied feature extraction, correct? And feature construction. We studied what is the vanishing gradient. We studied regularization techniques. We studied stochastic gradient descent, batch gradient descent, mini batch gradient descent. We studied cross validations, hold out validation. So we studied many topics, in fact. So please, you need to go to the slides from number 1 to number 8, and try to study all those concepts one more time, and try to summarize it. I mean, for the oral exam, I will not give you a problem to solve. In fact, I will just ask you about a concept. So I can ask you what is the difference between separable and inseparable data sets. Can we use, for example, a perceptron for solving inseparable data set, for example? How can we do this? What is the difference between autoencoder and the principal component analysis? What is error backpropagation? What is gradient descent? What is gradient ascent, right? What is learning rate? What is momentum turn? So please go to the slides and study those slides very carefully. And if you have any questions, just write down those questions and we can have a meeting one day. Or I wish if we can have a meeting in one of the labs in the campus, so we can discuss those questions. So if you have any questions, we can meet face to face, for example. The whole classroom in IMECO, we have a lab in the 6th floor. We can meet there and we can discuss those questions. We studied the concept, you have the code, you have all, you have all the material. So just please spend the time studying those topics and practice. Please practice programming and try to solve the problems. You have lots of projects. I mean, today I give you examples from data, from text, from machine vision, from time series. So you have lots of online. Also, you can find lots of stuff. So this is all for today. In fact, this is all for today. And the rest of the time today, please just try to work in the project. And if you have any questions, just call. I will be in the office until 4 or 4:30. Just if you have any questions, just send me an email or just call me. We can open. We can have more discussions. Mm-hmm. Yes. So do you have any questions? So I will stop this, live streaming.